The year was 1943, and the skies over Nazi-occupied Europe had become a deadly chessboard where technological superiority could mean the difference between victory and defeat. On a cold morning in early spring, German air defense crews scrambled as radar operators detected yet another incursion into their airspace. What happened next would lead to one of the most significant technological revelations of World War II. A British de Havilland Mosquito bomber had been hit by anti-aircraft fire over Germany. Unlike many aircraft that would have disintegrated under such punishment, the Mosquito managed to limp away from its target before finally crash-landing in a field outside a small German town. The wreckage was quickly secured by German military forces and transported to a specialized research facility where enemy aircraft were systematically analyzed for intelligence purposes. German engineers approached the wreckage with the methodical precision their nation had become famous for. They had examined countless Allied aircraft before: American B-17 Flying Fortresses with their heavy armor plating, British Lancasters with their robust aluminum construction. But as they began their initial inspection of the Mosquito, something immediately struck them as unusual. The aircraft felt different. The way the structure had failed, the pattern of damage, even the sound the material made when struck with a hammer, all of it was wrong for what they expected from an aircraft. Their confusion only deepened when they began to cut into the fuselage. Where they expected to find the familiar dull gray of aluminum alloy, they instead discovered layers of what appeared to be wood. But this wasn't ordinary wood. As they peeled back the layers, they found something that defied their understanding of aircraft construction. A sophisticated sandwich of wood veneers bonded together with some kind of adhesive, creating a structure that was demonstrating strength characteristics that seemed impossible for such a material. The initial reaction among the German engineering team was disbelief, followed quickly by contempt. The British, they assumed, must be so desperate for strategic materials that they had resorted to building their bombers out of furniture-grade materials. Aluminum was precious in wartime. Perhaps the British were simply running out? This theory seemed to make sense given the naval blockades and the intense resource demands of total war. But then the testing began, and everything the German engineers thought they knew about materials science was challenged. When they subjected samples of the Mosquito structure to stress tests, the results were shocking. This wooden construction was demonstrating strength-to-weight ratios that exceeded their best aluminum airframes. The material was lighter than metal, yet in many applications it proved to be stronger. Moreover, it had other properties that seemed almost magical. It absorbed vibrations better than metal, it was easier to repair in the field, and perhaps most remarkably, it was nearly invisible to the primitive radar systems of the era. What the Germans had discovered was plywood, but not the simple plywood that might be found in a carpenter's workshop. This was a highly engineered composite material that represented years of research and development by de Havilland and British material scientists. The British had created what would later be recognized as one of the world's first modern composite materials, a predecessor to the carbon fiber and advanced composites that would revolutionize industries decades later. The Mosquito itself had earned the nickname the Wooden Wonder among Allied aircrews, though the Germans had dismissed such reports as propaganda. Now, with pieces of the aircraft laid out before them in their laboratory, the German engineers had to confront an uncomfortable truth. The British hadn't built a wooden aircraft out of desperation. They had done it out of genius. This discovery set off alarm bells throughout the German military-industrial complex. Intelligence reports were hastily compiled and sent to Berlin. If the British could build aircraft this capable out of wood, what other technological advantages might they possess that German intelligence had overlooked? The Mosquito had already proven itself to be one of the most versatile aircraft of the war, serving as a bomber, fighter, night fighter, pathfinder, and reconnaissance platform. It was fast enough to outrun most German fighters, and crews reported that it could take significant damage and still make it home. What made this revelation even more concerning for the Germans was the implication for manufacturing. Wood was renewable and abundant, even in wartime Britain. The specialized aluminum alloys required for aircraft construction demanded complex supply chains, energy-intensive smelting operations, and access to raw materials that were increasingly difficult to obtain as the war progressed. The British had found a way to build world-class aircraft using materials that could be sourced from their own forests and processed in furniture factories and woodworking shops across the country. The story of what German engineers discovered when they cracked open that British bomber is more than just a tale of wartime espionage and technological surprise. It's a story about innovation born from constraint, about challenging assumptions, and about how sometimes the most advanced solution doesn't come from the newest technology, but from a radically different way of thinking about old materials. To understand why the German engineers were so astonished by what they found in the mosquito, we need to understand what made this plywood so special. This wasn't the material you might use to build a bookshelf or repair a fence. This was a carefully engineered composite that represented a revolution in materials science, even if few people at the time recognized it as such. Traditional plywood had been around since the 1850s. The basic concept was simple. Take thin sheets of wood veneer, stack them with the grain of each layer running perpendicular to the layers above and below, and glue them together. This cross-grain construction gave plywood some advantages over solid wood. It was more dimensionally stable, less prone to splitting, and could be made in large sheets. But it was still just wood, with all the limitations that implied. What de Havilland developed was something far more sophisticated. They used a specific type of wood, primarily birch with some spruce, selected for its exceptional strength-to-weight ratio. Birch wood, when properly prepared, has a tensile strength, resistance to being pulled apart, that approaches that of aluminum, but at a fraction of the weight. The key was in how these veneers were processed and combined. The wood was cut into extremely thin veneers, much thinner than standard plywood. Each sheet was carefully inspected for defects, knots, irregular grain, or any imperfections that might create weak points. Only the finest veneers made it into the aircraft construction. These sheets were then dried to a precise moisture content. Too much moisture and the wood would be weak and prone to rot. Too little and it would become brittle and prone to cracking. The real magic, however, was in the adhesive. De Havilland worked with a phenol formaldehyde resin, a synthetic polymer that was one of the first truly modern plastics. This wasn't traditional wood glue made from animal proteins. This was a thermosetting resin that, when heated and cured, formed extremely strong chemical bonds. The resin would penetrate into the wood fibers themselves, creating a bond that was actually stronger than the wood it connected. The manufacturing process was precise and demanding. Veneers were coated with the resin, stacked in the correct orientation, and then placed in large heated presses. Under carefully controlled temperature and pressure, the resin would cure, fusing the layers together into a unified structure. The result was a material where it was virtually impossible to separate the layers. You would tear the wood itself before you could pull the laminated layers apart. But de Havilland didn't stop there. They developed what's called a sandwich construction for critical structural elements. Imagine two thin but strong outer skins separated by a lightweight core material. In the mosquito's case, this core was often balsa wood or a cellular structure. This sandwich design is incredibly efficient from an engineering standpoint. The outer skins resist tension and compression forces, while the core keeps them separated and resists shear forces, forces that would try to slide the skins past each other. This sandwich construction is the same basic principle used in modern aircraft, spacecraft, and high-performance racing cars. Except today we use carbon fiber skins with honeycomb cores instead of plywood and balsa. The British had stumbled upon, or perhaps deliberately developed, a structural principle that would prove to be one of the most efficient ways to build lightweight, strong structures. The properties of this engineered plywood were remarkable. Strength-to-weight ratio. The material was lighter than aluminum but could match or exceed it in strength when properly designed. This meant the mosquito could be built lighter, allowing it to carry more fuel, fly faster, or carry heavier bomb loads. Fatigue resistance. Metal aircraft suffered from fatigue. Repeated stress cycles would cause microscopic cracks to form and propagate until eventually, the structure would fail catastrophically. The wooden composite structure of the mosquito was much more resistant to this kind of fatigue. The wood fibers would absorb and distribute stresses in ways that metal couldn't. Damage tolerance. When aluminum is damaged, cracks tend to propagate rapidly. A small crack can quickly become a catastrophic failure. The laminated wood structure of the mosquito tended to contain damage. A crack in one layer wouldn't necessarily propagate to adjacent layers, meaning the aircraft could sustain damage that would destroy a metal aircraft and still remain airworthy. Vibration damping. Wood naturally absorbs vibrations much better than metal. This made the Mosquito a smoother, more stable gun platform and reduced fatigue on both the aircraft structure and the crew. Radar transparency. This was perhaps an unintended benefit, but the wooden structure reflected radar waves much less effectively than metal aircraft. In an era when radar was just becoming a crucial tool for air defense, the Mosquito had a built-in stealth characteristic. Ease of repair. Damaged sections could be repaired with relatively simple woodworking tools and techniques. In remote airfields where specialized metalworking equipment might not be available, this was a significant advantage. Manufacturing flexibility. Furniture makers, boat builders, and woodworking shops could be quickly converted to produce Mosquito components. This distributed manufacturing capability made the production chain more resilient to bombing and allowed Britain to tap into a workforce with existing skills. When the German engineers tested the material and realized all these properties, they understood they weren't looking at a desperate improvisation. They were looking at a sophisticated engineered material that in many ways was superior to the metals they were using. The British had turned a perceived weakness, lack of aluminum, into a strength by completely rethinking what an aircraft could be made from. The material was only part of the story. The real genius of the Mosquito was how that material was integrated into an overall design philosophy that challenged every conventional assumption about what a bomber should be. To understand why the German discovery was so significant, we need to understand the aircraft itself and the radical thinking behind it. In the late 1930s, as war clouds gathered over Europe, the conventional wisdom about bomber design was firmly established. Bombers needed heavy defensive armament, multiple gun turrets, large crews to man those guns, and armor plating to protect against fighter attacks. They needed to fly in formation for mutual protection. The American B-17 Flying Fortress epitomized this philosophy, bristling with machine guns and carrying a crew of 10. Geoffrey de Havilland, the legendary British aircraft designer, looked at this conventional wisdom and decided it was wrong. His radical proposal: build a bomber so fast that it wouldn't need defensive guns at all. No turrets, no gunners, no armor plating. Just 2 engines, 2 crew members, and speed. Lots of speed. The Air Ministry, the British government body responsible for the Royal Air Force, was skeptical, to put it mildly. A bomber without guns? It seemed like suicide. But de Havilland had done his calculations. If an aircraft could fly at 400 miles per hour or faster, it would be faster than any fighter of the era. Enemy fighters wouldn't be able to catch it, so defensive guns would be unnecessary. And by eliminating all those guns, turrets, gunners, ammunition, and armor, the aircraft would be much lighter, which would make it faster still, creating a virtuous cycle. But there was a problem. Building an aircraft that fast with conventional metal construction would require enormous, heavy engines. The aircraft would need to be large to accommodate those engines, which would make it heavy, which would require even more power. De Havilland needed a way to build an airframe that was simultaneously large enough to be useful but light enough to achieve the necessary speed. The answer was wood. Specifically, the advanced plywood composite construction we discussed in the previous chapter. Wood offered a strength-to-weight ratio that could make his radical vision possible. But using wood also meant completely rethinking how an aircraft was designed and built. The Mosquito's fuselage was constructed in 2 halves, like a clamshell. Each half was built over a large mold as a single unified structure. Workers would lay up the plywood layers, building up the sandwich construction with the balsa core and multiple layers of birch plywood skin. The process was more like boat building than traditional aircraft construction. Once both halves were complete, they would be joined together at a seam running along the center of the aircraft. This method had several advantages. First, it was fast. Traditional metal aircraft were built up from thousands of individual parts: ribs, stringers, skin panels, each one separately manufactured and then assembled. The Mosquito's shell construction meant far fewer parts and much simpler assembly. Second, it created a very smooth aerodynamic surface. There were no rivet heads to create drag, no panel gaps. The smooth wooden surface was then covered with fabric and painted, creating an exceptionally clean airframe. The wings were equally innovative. They used a wooden spar, the main structural beam running the length of the wing, made of laminated wood. This spar was incredibly strong, it had to be, as it carried the primary flight loads and the weight of the engines. The wing ribs were also wooden, and the entire structure was covered with plywood skin. Like the fuselage, the construction method created a very rigid, light, and aerodynamically smooth structure. The wing design incorporated another innovation. The engines were buried within the wing structure rather than hung on external pylons. This reduced drag significantly and contributed to the aircraft's exceptional speed. The Mosquito used Rolls-Royce Merlin engines, the same engines that powered the legendary Spitfire fighter and would later power the American P-51 Mustang. These were powerful, reliable engines, but in the Mosquito's lightweight airframe, they provided spectacular performance. When the prototype first flew in November 1940, it exceeded even de Havilland's optimistic predictions. The aircraft was fast, faster than any bomber and faster than most fighters. It was also remarkably agile for a bomber, able to perform maneuvers that would have been impossible in a heavier aircraft. And it had excellent range, able to reach deep into Germany and return to Britain. The lack of defensive armament, initially seen as the design's greatest weakness, proved to be a strength. The German Luftwaffe fighter pilots quickly learned that chasing a Mosquito was usually futile. The wooden bomber could simply outrun its pursuers. There are numerous accounts of frustrated German pilots pushing their fighters to maximum speed, watching the Mosquito slowly pull away, untouchable. But the Mosquito wasn't just fast. It was also versatile in ways that astonished both its designers and its operators. The basic airframe could be adapted to fill almost any role the RAF needed. As a bomber, it could carry a 4,000-pound bomb load, the same as the much larger, heavier, and slower Lancaster bomber, but could do so while flying faster and higher. Mosquito bombers conducted precision daylight raids that would have been suicide missions for other aircraft. As a fighter bomber, equipped with cannons and rockets, it could strike ground targets with devastating accuracy. The aircraft's stability and smooth flight characteristics made it an excellent gun platform. As a night fighter equipped with radar, it became one of the most successful night interceptors of the war. The wooden construction's radar transparency didn't matter when the aircraft was carrying its own radar, and the speed and agility made it deadly against German bombers. As a reconnaissance aircraft equipped with cameras instead of bombs, it could photograph targets deep in enemy territory and return before fighters could intercept it. As a pathfinder, it could lead bomber formations to their targets, marking them with flares and bombs for the following waves of aircraft. This versatility meant that Britain could use the same basic airframe and production line to fill multiple critical roles. From a logistics and manufacturing standpoint, this was enormously efficient. The aircraft also proved remarkably survivable. Crews reported bringing home Mosquitoes with large sections of wing or fuselage shot away. The wooden construction could absorb battle damage that would have brought down a metal aircraft. There are accounts of Mosquitoes returning to base with one engine out, parts of the tail missing, and holes large enough to climb through in the wings, and still flying well enough for a safe landing. When German engineers examined the crashed Mosquito and realized all of this, they understood they were looking at more than just an interesting material choice. They were looking at a completely different philosophy of aircraft design, one that had proven itself in the most demanding testing ground imaginable, aerial combat. The discovery of the Mosquito's wooden construction created ripples throughout the German military and industrial establishment. Intelligence reports were compiled, meetings were held, and engineers were tasked with understanding how the British had achieved what the Germans had thought impossible. But the German response to this revelation tells us as much about the limitations of technological adaptation in wartime as it does about the brilliance of the original design. The first German reaction was to attempt to replicate the concept. If the British could build high-performance aircraft from wood, surely German engineering and manufacturing prowess could do the same, perhaps even better. Several German aircraft companies began exploring wooden construction techniques. The Focke-Wulf Ta-154, sometimes called the German Mosquito, was the most serious attempt. The Ta-154 was, on paper, quite similar to the Mosquito. It was a twin-engine, wooden construction aircraft designed to serve as a night fighter. The prototypes showed promise with good speed and handling characteristics. German engineers had studied captured Mosquito components and believed they understood the principles involved. But understanding principles and successfully implementing them proved to be very different things. The problems began with the adhesive. The phenol formaldehyde resin used in the mosquito was produced in Britain using specific formulations and manufacturing processes that the Germans didn't fully understand. German chemical companies attempted to create similar adhesives, but the results were inconsistent. Some batches worked well, others failed catastrophically. There are reports of Ta-154 aircraft literally coming apart in flight when the glue failed. Making matters worse, by 1943, when these programs were being developed, Germany was under intense strategic bombing. The chemical plants that could produce the specialized resins were priority targets for Allied bombers. Supply chains were disrupted, quality control became nearly impossible, and the manufacturing infrastructure necessary to produce high-quality wooden aircraft at scale simply couldn't be maintained. The Germans also lacked Britain's deep expertise in woodworking at an industrial scale. Britain had centuries of shipbuilding tradition, creating a workforce skilled in working with wood for demanding structural applications. The British furniture industry was sophisticated and extensive. Germany had these capabilities too, but not to the same extent, and by the middle of the war, skilled labor was in desperately short supply. There was also a cultural and institutional barrier. German aviation engineering had invested heavily in all-metal construction. The major aircraft manufacturers Messerschmitt, Heinkel, Junkers had built their reputations and their factories around metal aircraft. Switching to wooden construction would have meant retooling factories, retraining workers, and essentially starting over with new design methodologies. In the middle of a war that Germany was increasingly losing, there was neither time nor resources for such a fundamental shift. The Ta-154 program was eventually cancelled after only a small number of aircraft were built. Other German wooden aircraft projects met similar fates. The Germans had discovered the secret of the Mosquito's construction, but they couldn't successfully replicate it. This failure highlighted an important lesson about technology. Sometimes the most important aspects of an innovation aren't the ideas themselves, but the industrial ecosystem and knowledge base necessary to implement those ideas. But the German discovery of the Mosquito's construction had effects beyond direct attempts at replication. It forced German military planners to reconsider their assumptions about materials and manufacturing. Reports circulated highlighting how the British had turned a supposed limitation, shortage of aluminum, into an advantage by thinking creatively about materials. Some German engineers began to explore other composite materials and unconventional construction techniques. Late-war German aircraft like the Heinkel He-162 Volksjäger, People's Fighter, incorporated some wooden components as part of efforts to conserve strategic materials. These aircraft used metal where performance was critical and wood where it could work, creating hybrid designs that tried to get the best of both approaches. The Germans also learned important lessons about how their enemies were thinking about the war industrially. The Mosquito revealed that Britain was playing a long game, developing manufacturing strategies that were sustainable and scalable using domestic resources. This was a sharp contrast to Germany's approach, which relied heavily on conquered territories and forced labor to supply materials and production capacity. German intelligence also noted the Mosquito's distributed manufacturing model. Components were built in hundreds of small workshops and furniture factories across Britain, then transported to assembly facilities. This made the manufacturing chain remarkably resilient to bombing. Even if a final assembly plant was destroyed, the supply of components would continue. Germany had concentrated its aircraft production in large facilities that, while efficient in peacetime, were vulnerable to strategic bombing. The psychological impact of the Mosquito on the Luftwaffe was also significant. German fighter pilots, who had been trained to attack bombers with confidence, knowing their heavily armed Me-109s and FW-190s were faster and more maneuverable than the enemy bombers, found the Mosquito to be a frustrating exception. Numerous German pilot accounts from the war described the demoralizing experience of pursuing a Mosquito at full throttle, only to watch it accelerate away. German air defense planners had to develop specific tactics for dealing with Mosquitoes. These typically involved using their fastest fighters, often specially stripped-down versions, attempting to position them above the Mosquito's flight path so they could dive on it, the one scenario where they might have a speed advantage, or trying to catch Mosquitoes during their most vulnerable phases of flight, takeoff and landing. None of these tactics were particularly effective, and the Mosquito maintained the lowest loss rate of any Allied bomber throughout the war. The broader lesson from the German response to the Mosquito discovery was about the nature of technological advantage in warfare. It's not enough to know what your enemy is doing. You need the industrial capacity, the skilled workforce, the material supplies, and the time to actually implement competing solutions. By the time Germany fully understood what made the Mosquito so effective, it was too late to develop an effective response. There's also a lesson about the danger of technological orthodoxy. The German aviation industry was deeply committed to all-metal construction. This wasn't irrational. Metal aircraft had served them well, and German metallurgy was excellent. But this commitment made it difficult to recognize and adapt to a radically different approach. The Germans saw the Mosquito's wooden construction initially as a sign of British desperation, when in fact it was a sign of British ingenuity. The story of the German discovery also highlights how intelligence and reconnaissance, while valuable, must be coupled with the ability to act on that intelligence. The Germans learned the Mosquito's secrets relatively early in the war, but they couldn't translate that knowledge into comparable aircraft. Understanding your opponent's advantages is only the first step. Developing effective responses requires a functioning industrial base, resources, time, and often a willingness to challenge established ways of thinking. The discovery of the Mosquito's wooden construction represented something more significant than just an interesting wartime anecdote. It was an early glimpse of a materials revolution that would transform industries from aerospace to automotive to construction. To understand why this matters, we need to delve into the science of composite materials and why they're so important. A composite material is, at its most basic, any material made from two or more constituents with different properties that, when combined, create something with characteristics different from any of the individual components. The Mosquito's plywood was a composite, with fibers, providing strength, embedded in a resin matrix, holding everything together and transferring loads between fibers. The key to understanding composites is recognizing that many materials are strong in some ways but weak in others. Steel is strong in tension, you can pull on it, and compression, you can squeeze it, but it's heavy. Wood is strong in tension along the grain but weak across the grain and in compression. Plastics can be light and moldable but typically aren't very strong. The genius of composites is finding ways to combine materials so that the strengths of one compensate for the weaknesses of another. In the Mosquito's plywood, individual wood veneers were strong along their grain but weak across it. By stacking veneers with their grains oriented in different directions, the composite material became strong in all directions. The resin held everything together and allowed loads to be transferred between layers. This is the same basic principle behind modern composite materials, just with different constituents. The concept of strength-to-weight ratio is crucial here. Engineers don't just care about how strong a material is. They care about how strong it is relative to its weight. A steel beam might be very strong, but if you could build something equally strong from a material that weighs half as much, that's a huge advantage, especially in applications like aircraft where every pound matters. Modern composite materials have taken the principles demonstrated in the Mosquito to extraordinary levels. Carbon fiber reinforced polymer, CFRP, the material used in everything from Formula One race cars to commercial airliners to sporting equipment, works on the same basic principle as the Mosquito's plywood. Carbon fibers, incredibly strong in tension but brittle on their own, are embedded in an epoxy resin matrix. The result is a material that's lighter than aluminum but can be stronger than steel. The properties of composites can be tailored by changing how the reinforcing fibers are oriented. In the Mosquito, the wood grain orientation in each layer was carefully controlled. In modern composites, engineers do something similar with carbon fiber. They can orient the fibers precisely where strength is needed in specific directions. This is called anisotropic design, creating materials that have different properties in different directions. A car manufacturer building a race car, for example, might design the carbon fiber monocoque, the main structural shell, to be extremely strong in certain directions where crash loads will occur, while being lighter and more flexible in other directions where such strength isn't needed. This level of optimization is difficult or impossible with traditional materials like steel or aluminum, which have the same properties in all directions. They're isotropic. Another critical property of composites that the Mosquito demonstrated is damage tolerance. When metal structures are damaged, cracks tend to propagate. A small crack concentrates stress at its tip, causing it to grow, which concentrates more stress, causing it to grow faster. A vicious cycle that can lead to catastrophic failure. This is called fatigue failure, and it's been responsible for numerous structural failures throughout history, from aircraft crashes to bridge collapses. Composites behave differently. In the Mosquito's plywood, a crack in one layer didn't automatically propagate to adjacent layers because the resin between layers could absorb some of the stress. In modern fiber composites, damage tends to be contained because the resin matrix can crack without necessarily breaking the fibers, and breaks in some fibers don't automatically propagate to adjacent fibers. This makes composite structures more damage tolerant and resistant to fatigue. Composites also offer advantages in manufacturing. The Mosquito's shell construction, where large sections of the aircraft were formed in molds, presaged modern composite manufacturing techniques. Today, entire aircraft fuselage sections can be manufactured as single pieces using composite materials, eliminating thousands of fasteners and creating stronger, lighter, more aerodynamic structures. The Boeing 787 Dreamliner, for instance, is built primarily from composite materials. About 50% of the aircraft by weight is composites, including the fuselage and wings. This extensive use of composites allows the 787 to be lighter, more fuel efficient, and more resistant to corrosion than traditional metal aircraft. Passengers benefit too. The composite structure allows for higher cabin pressure and humidity, reducing jet lag and improving comfort. But composites aren't perfect, and the challenges the Germans faced in trying to replicate the Mosquito highlight some of these limitations. Composites are often more difficult to manufacture than metals. The processes require precise control of temperatures, pressures, and curing times. Quality control is critical. A poorly made composite can fail catastrophically, and defects aren't always visible. Repair is also more complex. A metal structure can often be repaired by riveting on a patch or welding new material in place. Composite repairs typically require specialized materials and procedures, and the repaired area may never be quite as strong as the original structure. Environmental factors can affect composites in ways they don't affect metals. Moisture absorption can degrade some resin systems. Temperature extremes can cause problems. Some resins become brittle in extreme cold or soften in extreme heat. The Mosquito, for instance, had to be carefully maintained to prevent moisture from degrading the wood and glue bonds. Aircraft serving in tropical climates required special attention to prevent fungal growth and delamination. Cost is another consideration. While composite materials can save money over the life of a product through reduced weight and increased durability, the initial manufacturing costs are often higher than for traditional materials. This requires a long-term perspective that isn't always easy to maintain in competitive industries. Despite these challenges, composite materials have become ubiquitous in high-performance applications. They're used in aircraft and spacecraft, high-speed trains, racing cars, wind turbine blades, sporting equipment, prosthetic limbs, and countless other applications where strength, lightweight, or specific performance characteristics are critical. The Mosquito's wooden construction was an early example of composite material design, even if the engineers at de Havilland didn't use that terminology. They empirically discovered principles that material scientists would later formalize and extend. When German engineers cracked open that crashed bomber and found wood instead of metal, they were getting their first glimpse of a future where advanced composites would revolutionize manufacturing across industries. One of the most fascinating aspects of the Mosquito story is what it reveals about the nature of innovation. The aircraft wasn't developed because British engineers had access to amazing new materials or unlimited resources. It was developed precisely because they lacked these things. The Mosquito is a perfect case study in how constraints can drive innovation in unexpected directions. In 1938, when Geoffrey de Havilland began seriously developing the concept that would become the Mosquito, Britain was facing a strategic materials crisis that would only worsen with the outbreak of war. Aluminum was essential for aircraft construction, but Britain had limited domestic aluminum production. The country had to import bauxite, the ore from which aluminum is refined, from distant sources, ship it across ocean lanes that would soon be threatened by German U-boats, and process it using energy-intensive smelting operations. Every pound of aluminum that went into aircraft construction was a pound that couldn't be used for other military applications. The Royal Navy needed aluminum for ships. The Army needed it for vehicles. There was constant competition for this critical resource. Any aircraft design that could reduce aluminum consumption would free up this strategic material for other uses. At the same time, Britain had abundant forests and a sophisticated woodworking industry. Centuries of shipbuilding had created deep expertise in working with wood for structural applications. The furniture industry employed skilled craftsmen who understood wood's properties and how to work it. These resources were being underutilized for the war effort because conventional thinking said that modern aircraft had to be built from metal. De Havilland's genius was recognizing that this constraint, limited aluminum availability, could be reframed as an opportunity. Instead of trying to compete for scarce aluminum, why not use a material that was abundant, renewable, and domestic? Instead of building aircraft in specialized aviation factories that were targets for enemy bombers, why not distribute production across hundreds of woodworking shops that would be much harder to disrupt? This kind of thinking, reframing constraints as opportunities, is at the heart of many important innovations. When resources are unlimited, there's often little incentive to think creatively. The path of least resistance is to do what's always been done, perhaps with incremental improvements. But when conventional approaches are impossible due to constraints, innovators are forced to think differently. The Mosquito project also benefited from another type of constraint: skepticism from the establishment. The Air Ministry was initially very resistant to de Havilland's wooden bomber concept. They wanted aircraft that looked like aircraft, metal construction, defensive armament, large crews. De Havilland had to fight for every resource, every test flight, every opportunity to prove his concept. This skepticism might seem like a purely negative factor, but it actually had some benefits. Because the project was somewhat outside the mainstream of British aviation development, de Havilland had more freedom to experiment. He wasn't bound by the same bureaucratic requirements and design standards that governed more conventional aircraft programs. This allowed him to make radical choices that might not have been permitted in a higher-profile program. The constraint of working with wood also forced innovations that turned out to have unexpected benefits. The shell construction technique, developed because it was the most efficient way to work with plywood, created a smooth, aerodynamic surface that contributed to the aircraft's exceptional speed. The distributed manufacturing model, adopted because it made sense for wooden construction, created resilience against bombing that centralized metal aircraft production couldn't match. There's a broader lesson here about how institutions respond to innovation. The military establishment initially resisted the Mosquito because it violated their mental models of what a bomber should be. They had theories about air combat that emphasized defensive firepower and formation flying. An unarmed bomber that relied on speed and would operate alone didn't fit these theories. But theories, no matter how elegant, have to yield to evidence. Once the Mosquito began operational service and proved its capabilities, attitudes changed rapidly. The aircraft that had struggled to get funding and support suddenly became one of the most prized platforms in the RAF. Production was ramped up as quickly as possible, and new roles were constantly being found for the versatile aircraft. This pattern, initial resistance to radical innovation followed by rapid adoption once success is demonstrated, is common across many fields. Established institutions naturally resist ideas that challenge their existing practices and beliefs. This resistance isn't always irrational. Most radical new ideas actually do fail. But it means that truly innovative concepts often have to succeed despite institutional skepticism rather than because of institutional support. The Germans, observing the Mosquito's success, faced their own constraints in responding. By the time they fully understood what made the Mosquito special, Germany was facing increasing resource shortages, workforce limitations, and strategic bombing that disrupted their industrial capacity. They were constrained in different ways than Britain had been, and those constraints made it effectively impossible to develop an equivalent aircraft. This highlights another important point about innovation. Timing matters. Britain developed the Mosquito relatively early in the war, when they still had time to experiment, iterate, and refine the design. By the time Germany tried to respond, They were in a much more desperate situation where they couldn't afford the time and resources necessary to develop new manufacturing techniques and supply chains. The mosquito story also illustrates the importance of institutional knowledge and expertise. Britain's wooden aircraft construction relied on centuries of accumulated knowledge about working with wood. This knowledge was embedded in the workforce, in training systems, in the practices of shipyards and furniture makers. It wasn't something that could be quickly replicated even if you understood the principles intellectually. Germany had engineering talent and scientific knowledge equal to Britain's, but they lacked the specific industrial ecosystem that made the mosquito possible. This shows that innovation isn't just about having smart people or good ideas, it's about having the right combination of knowledge, infrastructure, workforce skills, and industrial capacity. Britain could build wooden aircraft not just because de Havilland was clever, but because there was an entire industrial ecosystem ready to support that approach. There's also an important lesson about the relationship between military and civilian technology. The mosquito succeeded partly because it could leverage civilian industries, furniture making, boat building, woodworking, that had been perfected for entirely different purposes. The skills needed to build fine furniture or wooden boats translated surprisingly well to building aircraft. This is an early example of what we now call dual-use technology, where civilian and military applications share common technical foundations. Modern militaries still struggle with the balance between specialized military technology and leveraging civilian industrial capacity. The most successful military systems often aren't the ones designed from scratch for military use, but rather adaptations of civilian technologies. The smartphone revolution, for instance, has enabled all sorts of military applications that would have been impossible with purely military design systems. The constraint-driven innovation that produced the mosquito also teaches us about the danger of premature optimization. If Britain had had unlimited aluminum, they might never have explored wooden construction. They would have optimized their existing metal aircraft designs, making them incrementally better but never discovering the radical performance advantages that the wooden mosquito offered.